Yes, I'm audible to both of you. Martin and Harsha, where were you? Harsha?
Ma'am, I was outside. I just reached home.
Okay. Let's start with capillarity. This is the last topic of your hydrostatics. Now, angle of contact I have to discuss. See, if you take a liquid column, fine, in that liquid column, there will be the uppermost portion of the fluid. Correct? There will be this uppermost portion of the fluid. Now see, this fluid is making some angle with the wall of the container. That angle is known as angle of contact. So see class, suppose this is the meniscus that we have obtained. So this is a concave meniscus. So see, just drop a tangent at the surface. Now this tangent, because how will you measure the angle without knowing the tangent? So mark the tangent, drop a tangent and take the angle with the container. This is theta. This is the angle of contact for concave meniscus. Similarly, this is convex. Now look, if I'll drop a tangent and I have to measure this, so this is theta. This angle is theta. Fine, we take it from inside the liquid, not this part. Otherwise, we could have taken this also. This is also container. We'll consider the portion which is included in the fluids. And this is a plane meniscus. So see, drop a tangent. And look, this is always form 90 degree. Fine. So yes, let me read out the points which are written. Angle of contact, the angle between a liquid and a solid is known as the angle theta, which the tangent to the liquid surface at the point of contact makes with the solid surface inside the liquid. This is important. Otherwise, you will be confused whether you have to consider this angle or this angle. Fine. So the angle of contact depends on the following factors: nature of the liquid and the solid in contact. It depends upon the type, because why? Reason is that different types of fluid, different types of liquid will be forming different types of meniscus in your system. That's why. And the medium that exists above the free surface of liquid means this medium, this portion. Fine. Impurities present in the liquid, angle of contact decreases on adding impurities in the liquid. Suppose this is the angle of contact. Now I have added some particles. This meniscus will become deeper. This will become deeper. So angle of contact will decrease. And if it's a convex, it will become steeper. So angle of this will again decrease. And temperature is directly proportional. See, two things are there. Impurities, angle of contact depends on two things. Just remember it like this. Angle of contact depends on two things. You have impurities and you have temperature. This is inversely proportional to angle of contact is inversely proportional to impurities. You add more impurities, angle of contact will decrease. Fine. But temperature is directly proportional to it. You increase the temperature, angle of contact will increase. You decrease the temperature, angle of contact will decrease. Fine. Now look, this is about the angle of contact in different types of meniscus. If the theta is acute, like in this case, look, this is a concave upwards meniscus. I have dropped the tangent. This is angle. Look, this is the angle of contact. So see, this is always acute. Whenever you will drop, and if it's concave upwards, it will always form this small angle. Right? This small angle will be formed, which will always be acute. An acute angle means less than 90 degree, right? So in this case, you have the adhesive forces stronger than the cohesive forces. So best example is water in glass. If you take a glass, you filled it with water, the adhesive forces are stronger. This I have discussed in the last class also initially. right? So liquid will wet the walls of the container. So in such cases, you have the angle as acute. Fine. So the conclusion points are liquid will wet the solid, meniscus of the liquid will be concave, and liquid will rise in the capillary tube made of such a solid. Regarding capillary tube, I'll discuss, then only this will be clear. But before capillarity started, capillary tube we get to know about, we'll have to discuss these. Suppose this is convex upwards. This is convex upwards. So look, this is the angle of contact. Can you see this is greater than 90 degree? It's like 120, 140, like this angle. This is always 90 degree. Here the cohesive forces are greater than adhesive forces. In such cases only you get the convex upwards meniscus. So here the liquid will not wet. Like mercury kept in glass, the entire mercury gets wiped off through the glass. Not a single drop is left within the glass. So concluding points, liquid will not wet the solid, meniscus of the liquid will be convex, and liquid will depressed in the capillary tube made of such a solid. These 2 points, I'll explain in the last. Once we'll start with capillarity, then I'll explain. Angle of contact is plane, yes, see. So here theta is 90 degree. Fine, this is known as flat meniscus, plane meniscus, or flat meniscus, fine. So adhesive forces is equal to the cohesive force. Adhesive forces are equal to cohesive forces. Like normal silver glass you take and put them in water. Fine. Here the adhesive forces and cohesive forces both are same. All right, write down these points regarding angle of contact first. The first heading here is angle of contact. Then we'll start with capillarity.
Ma'am, cohesive forces means between water and the glass.
Yes, Harsha, what you're asking?
Ma'am, cohesive forces means between water and the glass.
No, that is adhesive. Between different objects, it's adhesive. Between same, it's cohesive.
Okay. Yes, in the last point, liquid will rise in the capillary fluid made of such a solid.
Yes, Harsha?
Could you explain the last point? Liquid will rise in the capillary tube.
This I will explain in capillarity. We have not started capillarity, no? That's why. That's what I was saying. These two last point, no? This one and this one. I'll explain after this. Okay.
Okay.
Now look what is meant by capillarity, then you will understand those 2 points also. So suppose I have taken a container. Fine, and I have filled it. And I have filled it completely with water. Right? And now if I take a thick tube, suppose I have taken this tube. Suppose I have taken this tube. Fine. So some amount of water will go in here also. This part will also be having water. Now suppose if I take a very, very thin tube. A very thin tube. So in this tube, what happens? Instead of the water level being at the same, this rises. The water level no, here in this tube will rise. All right. Like the best example is if you take water here. Or one more example, let's take. I have taken this container. I have filled it completely with fluid. Now this fluid this time is mercury. Now again I am taking a very thin tube in this. What am I noticing is that the fluid which is present in this now is decreasing here. This is the maximum length reached. Now look, this phenomena of rise of the liquid or fall of the liquid in a very thin tube, and we call this narrow tube as the capillary tube. This tube, this is known as the capillary tube. This thin tube, rise or fall of liquid, this is known as capillarity. We have a full derivation for it. You will understand in there. I'll explain this. So this rise and fall. Now come to those points. Liquid will rise and fall where? See, I gave you example of water and mercury. So first example was of water in glass. Liquid will rise in capillary tube made of such a solid. Means this. In wherever angle of contact is acute and concave upwards meniscus is formed, that is, adhesive forces are greater than cohesive forces, liquid will rise because we have two conditions, whether it will rise or it will fall. And in such cases where angle of contact is obtuse, liquid will get depressed in the capillary tube made of such a solid. Fine. So this is known as angle of contact, which is present in the capillary tube where cohesive forces are greater. So that is what is meant by liquid will get depressed. Now these points are clear to you. Liquid will rise and liquid will be depressed. To both of you, Martin, Harsha. Clear or not?
Yes, ma'am.
Okay. That's what was the meaning of it. Now coming to see derivation is there, and this capillary rise ascent formula, this is a little longer formula, and sometimes this comes with your application based questions also in your 5 markers. So this is a little important, but not very difficult because you have been studying about all the pressures in hydrostatic till now. Now suppose here again a container has been taken. Suppose here we have taken a container. Fine. Now look here, I have filled this container with a fluid. Now I have taken a very thin capillary tube. Capillary tube are in any ways narrower only. If you've seen them, they are very narrow. Now also I'm considering some points. This is point A. This is one point B at the tip, and here is also one point within, that is point C. Different points. Look, this is exactly at the surface where the atmospheric pressure is only acting at this point A. Here There will be excess pressure also here because of the capillary tube, as well as there will be atmospheric pressure also, correct? Excess pressure will also be there, and pressure due to the liquid column will also be there, which we have studied, correct? And at this point, see, here also we'll be having P naught. Atmospheric pressure will be occurring at this point also. Why have I taken this? So that we have all the types of cases. A point exactly on the surface, a point exactly on the depth of the capillary tube, a point exactly on the depth but without the capillary. So we have all the points present.
Ma'am, point C also will have atmospheric pressure.
Point C will also have atmospheric pressure. Yes, yes. Point C will also be having. See, C is just taken at the level of P. Fine, C is just taken at the level of P. Atmospheric pressure will be existing. Atmospheric pressure will be there in all the three because this is open. Open container we have taken. Understood? Since we have taken an open container, that's why we are having P naught everywhere. Now, where the difference will come, you will see. Let's start with one by one. Okay, what's this? On introducing capillary tube in liquid, pressure at convex side is less than concave side. See, this is all about excess pressure. This means this meniscus that has been formed. So pressure at the convex side is less than. Here, more pressure is being exerted wherever the meniscus has been formed. Over the concave side, over the convex side, this side pressure is less. Here it's more. Because pressure due to liquid column will also be acting. Pressure due to excess pressure will also be acting. Atmospheric will be acting. That's what has been mentioned. Now, when we're talking about a pressure at A, this is not difficult. Pressure at A is simply P naught only, which is the atmospheric pressure. This is the atmospheric pressure. That's it. Fine. When we're talking about pressure at B point, we are considering, we'll not talk about, we'll be talking about H rho G, but we'll see it later. First, let us see if there is just this point, B point. I'll be talking about H rho G also, but let me just take the B point separately. Now, at B point, if I'm just talking about the pressure that is being exerted, I'm not including the pressure exerted by liquid column. I'll be having atmospheric pressure minus 2s by r. Why 2s divided by r? Because 2s by r is excess of pressure. Now the question comes, why subtraction? Why it has been subtracted? Because two pressures are acting on it. Fine, two pressures are acting in two different directions. The pressure, and one more thing, this S is basically the surface tension. I hope you remember. S is surface tension. So at B point you are taking, this is acting at a depth. Fine. Excess pressure is acting outward, upwards. That's why we have subtracted it. And instead of writing this, it's better if we write directly this as, see, if we directly write this PB as P naught minus 2s by r in order to make things clear. I'm writing this step by step so that all the things are made clear. Now, if we take point C outside the capillary tube at the same level as that of B, the level where the water has been considered is same. Point B is taken just at the same level, Pascal's law, if you remember. So pressure at C, individual pressure at C is P naught. That is the individual pressure at C. Now, pressure differences will be there. This is PB is there, P naught is present. So due to this pressure difference, fluid will flow from C to B till pressure at C is equal to pressure at B. Now, what is meant by this line? Due to the pressure difference, fluid flow from C to B till pressure at C is equal to pressure at B. This basically means this is the application of Pascal's law. Whatever is the pressure at B will be equal to the pressure at C. Since you have already done Pascal's law, we are not focusing on that. This is what is meant by that. Now, actual, let's finally write what is the complete PB that is acting. P naught minus 2s by r is acting, but pressure due to the liquid column is acting in the same direction. So we will add H rho G. We will be adding H rho G because pressure due to the liquid column is acting in the same direction. Now, because of Pascal, what is the statement saying? If we take a point C, this is at the same level. There's a pressure difference that is acting. This atmospheric pressure is there and this pressure is there. This will be pushing it. Here also some pressures will be exerted and this will push it high. That's why the liquid column goes up. Now see, till when it will stop? How much liquid can flow in this? There's a possibility, we have to know when will this stop. When this pressure at B point will also be balancing the atmospheric pressure, then it will stop. It will become a condition of hydrostatic back, right? So that's why flow of liquid will stop when this PB is also equal to the P naught, which is the atmospheric pressure. I'm not writing it separately. This is PB is equal to P naught. So instead of this PB, I'll write this as P naught, which is equal to P naught minus 2S by R plus H rho G. Fine, H rho G. So P naught will be cancelled. Now look, H rho G is equal to 2S by R. From here, what do we have to find out? We have to find out how much the liquid has risen. So height is 2S divided by rho G R. This is the value of height, which is this is the value of the height of the liquid column. This is R. Fine. So what all variables are here? H is the height. This formula you have to remember. S is the surface tension and R. What is this R? Is the R radius of the tube, radius of meniscus? What have we considered? This R is the radius of the meniscus. S is surface tension, rho is density. Fine, let me write it. All these variables. H is the height. H is the height of the liquid column. S is the surface tension. Rho is density. G is acceleration due to gravity. This is radius of meniscus. There is one modification in this also, but it will be a lot to discuss in one go. First, you write this down, the entire derivation, get it clarified. I'm here. I'll be discussing this. Then I'll discuss one more thing. There's a modification in this formula that also comes. Because there are two angles, there are two radii present. One is your tube. This is also having its own radius, correct? And one is the radius of this meniscus. If the meniscus is like this, it must also be having a certain radius. So two different radii are present. That's why there's a whole lot derivation. Write it down first. I'll discuss it.
Why does point A not have excess pressure?
Why will point A have an excess pressure? Here, no bubble has been formed. Right. This is just we have not considered any bubble. This is just a point that is taken. This A is not a bubble that has been drawn. You get the excess pressure inside a bubble drop only, no? Like here at the tip of the capillary tube, you are getting a meniscus, which is in the form of circle. So excess pressure is there. A is just fluid, which is open to atmosphere. Neither there is pressure of the liquid also above it because there is no liquid above it, and nor there is any bubble formation, so that excess pressure will be existing. Only it is simply fluid is taken. It's like you take a glass filled with water, the upper superficial surface of the water present in the glass, it will be having atmospheric pressure only. The pressure due to the entire atmosphere will be acting on it. That's it.
Will
Fine, Harsha.
points we have it?
Point C will also be not having. We are not considering bubble.
Okay.
Okay. It's just that A and C point are just taken at separate depths, just in order to ensure that all the points we are taking. At A point, even if you take, at C point also take, only the pressure is being acted, right? And since, see, on C point, pressure due to liquid column is also acting. That is also acting. Excess pressure will not act, but due to liquid column will be acting. So in any ways, we are equating it to B because of Pascal's law, right? Both the C point and the tube are equated. So that's why excess pressure and the liquid column is already considered. Clear, Harsha?
Yes, ma'am. So there won't be a pressure difference when the tube is large.
In which tubes? Which points you're saying?
Ma'am, like in the first figure, the first tube which is bigger, it
This
doesn't
one.
have. Yes, ma'am.
See, it's like this tube is not having any capillarity phenomena occurring. This is a tube of a wider diameter. So in this, what will happen? It's like if you take a very thick tube and just keep it in water, you will never see any liquid rising up. You will just see the liquid is exactly at the same level as it was before. When you narrow the diameter, you take a very narrow tube with a very small diameter, like this also has an example in biology. Xylem also takes up the water and something from the ground. So due to the phenomenon of capillarity, because the xylem's diameter is very narrower. So in this case also, and if you perform, there are experiments also, very thin tube this is, and you just keep it in water, not water
So
any
they won't have excess
will
pressure
rise.
if it's a large tube.
Excess pressure over here.
Yes.
Yes, excess pressure will be there. Here, excess pressure will be there. It's just that this has not risen, so there is no capillarity. That's why we are not discussing it. This is the general case which we have already studied, which we have been studying. We have been studying this only, no, liquid column, liquid column, liquid column every time. It's just that this is a modification which we have studied, that if the tube is very narrow, then what will happen? Then capillarity will happen, will occur. Here, atmospheric pressure will also exist in the wider tube. Here, excess liquid due to the pressure due to liquid column will also be existing. Atmospheric pressure, all the phenomena which we have studied is valid for this. It's just that this is a new tube that we have taken.
Okay. Ma'am, C will also have pressure due to liquid column, right? Then
Yes,
why
yes,
we not
C will also have pressure.
we won't be considering that.
It won't be just, it's just that pressure at C is P naught, that was just telling you that there's a pressure difference created because excess pressure is over here. In C, you just have this part. You can write minus 2s by r. It's just that, no, it will become same. But the point of surface tension and the point of calculation, that is different. So that's why I didn't mention it can be P naught minus 2s by r. You can write it. It's just that I was telling you that at point A and at point C, it's these points are open to atmosphere and though no tube is present. But in any ways, difference is there. That's why we are having and C point is equal to PV only.
Okay, ma'am.
Look, now see, till here you have written. Now there's a modification which I was telling you, that two radii are present. Now just focus on this. Let me draw the figure first. We have a tube. So this is a capillary tube. Now the capillary tube will also be having its own radius, correct? The radius of capillary tube is also existing. So let's say this is this point, the center of the capillary tube. Center of the tube is taken as O1. So center of the tube is taken as O1, and the radius of the tube is taken as small r. So this is small r. Fine. Now, when I'm talking about the meniscus, look, this is the suppose edge of meniscus. So meniscus, if I complete it, look here, we just see this portion of meniscus, right? So I have completed the meniscus. This is the meniscus edge only, concave meniscus like this. I have just completed it. Okay. Now center of the meniscus. This center of meniscus must be somewhere here. I have not drawn it properly. It's on the back side. So it would be somewhere here like this. If you draw it properly, you will see it. And there is this radius of this meniscus, which is capital R. These things are present. It's a very, very slight, small derivation just to keep in mind. Now we'll join this and make it a triangle. Let's name this point as M so that this becomes one triangle. And let's take this angle as theta. Now, if you see in triangle O, O1, OM, cos theta is equal to, cos theta is what? Cos theta is base by hypotenuse. So base is R, hypotenuse is capital R. So small r by capital R. What is the radius of menisci equal to? R by cos theta. Now let's put this value here. So height of meniscus, this is the common formula which is used. 2s cos theta will go up and you have r rho g in the denominator. Fine. Now this small r that we are writing, this is the radius of tube. So most of the questions that are asked to you in the exam are based on this formula. Cos theta will be there. Rarely you have the question based on radius of meniscus. Radius of tube is only given. Write it down. We'll also see some questions. We'll see some practical applications of capillarity that is also left to be discussed. First, write down this page.
So in the question, they'll give us the angle between both the radii.
Yes. The angle will be given between both the radii of meniscus. Otherwise, the question height will be given and theta will be asked.
Okay.
See, rise of this comes as a theoretical question, conceptual question. Rise of liquid in a tube of insufficient length. So see, usually this comes to if the pressure differences are there and the liquid is getting filled up in the capillary tube. Suppose this is the capillary tube and the liquid is getting filled. So the question that arises is that this is getting filled completely, this is getting filled. Now, if suppose this was the initial level of the fluid, this was the initial level. And now after inserting this, the level has risen to this. Let's say we have not taken this out and it has reached the tip. So a doubt comes that will it emerge in the form of fountain? Like all the water will go up from the tip, all the water go up like a fountain? Answer to this is no. Here what happens, all of this gets stuck towards the end. It will not rise in the form of capillary tube. Fine, it will just stick over here, but it will not fall off. It will not fall down. All right. So radius of menisci increases, liquid does not spill. This is the conclusion. Let me write it. Radius of meniscus it's just that this radius of meniscus, this will increase. This will increase so that liquid does not spill. This is the condition. And then, so rise of liquid in a tube of insufficient length, liquid cannot emerge in the form of fountain from the upper end of a short capillary tube. It is because it will violate the law of conservation of energy. So in order to maintain it, radius of menisci will increase. Practical applications of capillarity. Oil rises in the cotton wicks of lamps through the small capillaries between the threads. You must have seen those diyas and these cotton wicks are kept. Oil is there. When you keep the oil, quickly this is soaked by the cotton. That is because of the capillary action of it. And we make the cotton wick also very thin by rubbing and rolling it through our fingers. We make it very thin. Water rises in the plant's leaves through fine pores of fibers of wood. So I think xylem it is, which takes up the water from the ground. And see, the stems are very narrower. So it takes it up. So one application is this. Writing nib is split in the middle so that a fine capillary is formed in it. Ink rises in the capillary. This means, have you seen the tips of those fountain pens? Isn't it like this? And then the top of the pen. This is like this. There's a small slit if you see. So that capillarity action can be done. A small, very small capillary tube can be created. So as soon as you dip it into the ink, this quickly absorbs all the ink. Clear? All these points are clear?
Yes, ma'am.
Okay. One more note point that I want to discuss. This will come as a separate question and practical applications will come as a separate question. One more thing that you have to understand is that, see, rise of liquid in a tube is inversely proportional to radius. How? H is equal to 2s cos theta r rho g. So height is inversely proportional to radius. All right. This basically means, and one more thing, there's a correlation with angle. If your angle is positive, height will be positive. Angle is negative, height will be negative. These are some points which will help in the exam. See, if theta is acute, which is less than 90 degree, theta is less than 90 degree. Like the example that I have been taking, water, best example. So height will also be positive. It means water will rise. This is the reason, and these were the connections which we were doing in angle of contact. Angle of contact acute, height of water rises. Remember that line? I think you had doubt also in that. This is that point. And similarly, if you take obtuse angle, that is theta is greater than 90 degree. Example, Mercury. So here height will be negative by the calculation, which will show that this will fall off. Clear? All these points are there. Write it down. Theory points are also a lot in this to be discussed. This you have written, no? From here you have to write.
Here theta is angle of contact.
Yes, this angle. This angle you're talking.
Yes, ma'am. Is it angle of contact?
No. This is angle between the radii only. This I was
Okay.
saying, this is in relation to angle. If this is not, that we have already discussed. Why would I write it differently? This is this angle between both the radii of meniscus and radii of tube. I was saying this is again relating to the fact which we studied in angle. Height rises or height depresses.
Okay.